A black hole is a region in space where the gravitational pull is so strong that nothing, not even light, can escape from it. This immense gravitational force arises because a large amount of matter is concentrated in an incredibly small area. The boundary surrounding a black hole is called the event horizon, the point beyond which nothing can escape. Black holes are formed when a massive star runs out of fuel and undergoes gravitational collapse. This occurs when the star's core contracts and the outer layers are blown off in a supernova explosion. If the remaining core mass is large enough, it can collapse into a singularity, a point of infinite density with a gravitational field so strong that it warps space-time around it. A black hole is typically formed in the following steps. Star's life cycle. A massive star, at least 10 to 20 times the mass of the Sun, goes through its life cycle, using nuclear fusion to convert hydrogen into heavier elements like helium, carbon, and oxygen. As fusion slows down, the star no longer has the energy to support itself against gravitational collapse. Supernova explosion. When fusion can no longer counteract gravity, the star's core collapses. The outer layers are ejected in a powerful explosion called a supernova. The core that remains after the explosion might be dense enough to collapse further. Gravitational collapse. If the remaining core has a mass greater than the Tolman-Oppenheimer-Volkoff limit, about 2 to 3 times the mass of the Sun, it will continue collapsing under its own gravity, eventually forming a singularity. Singularity formation. The core contracts to a point where its density becomes infinite and space-time is warped to such an extent that it forms a black hole. A black hole is formed at the end of the life cycle of a massive star, which typically occurs after billions of years. The exact time varies depending on the size and type of the star, but black holes are not something that can appear quickly. They require a long process of stellar evolution. Black holes can form anywhere in the universe, but they are most commonly found in regions with a large number of massive stars, such as star clusters, in dense areas of space with many stars, such as globular clusters and galactic centers. Many galaxies, including our own Milky Way, have supermassive black holes at their centers. These black holes are millions to billions of times the mass of the Sun. For example, Cygnus X1 is one of the most well-known stellar mass black holes in the Milky Way, formed from a massive star, Sagittarius. A** is the supermassive black hole at the center of our Milky Way galaxy. The closest known black hole to Earth is about 1,000 light-years away in the system called AA062000. This is still very far out of reach for current space exploration. While there are many black holes in the universe, they are generally spread out across vast distances, and the probability of a spacecraft or astronaut encountering one is extremely low. We have not yet developed the technology to travel to the vicinity of a black hole, and no spacecraft has been sent to explore black holes directly. Our current missions focus on studying black holes from afar using telescopes and other remote observation techniques. If a spaceship were to approach a black hole, several things would happen as it gets closer. As the spaceship gets closer to the black hole, the difference in gravitational pull between the front and the back of the spaceship, known as tidal forces, would stretch and compress it. This stretching effect, called spaghettification, would rip the spaceship apart long before it reaches the event horizon if it's too close to a supermassive black hole. For stellar mass black holes, these forces could become lethal at a distance of several thousand kilometers from the event horizon. From the perspective of an outside observer, the closer the spaceship gets to the event horizon, the slower its movement would appear. Time dilation due to the immense gravity near the black hole would cause time for the spaceship to slow down as it approaches the event horizon. The ship's crew would perceive time normally, but to an external observer it would seem to freeze as the ship approaches the event horizon. If the spaceship were to cross the event horizon, it would be unable to escape. Inside the event horizon, the curvature of space-time is so severe that all paths lead inward toward the singularity. No information, including light, can escape from this region, meaning the spaceship and its crew would be lost forever. Once past the event horizon, the crew would ultimately fall toward the singularity, where the laws of physics break down. The intense gravitational forces would cause the ship and everything inside it to be crushed to an infinitely small point at the singularity. In this region, the concept of space and time as we know them cease to function normally. In summary, if a spaceship gets too close to a black hole, it would experience stretching and potentially be torn apart by tidal forces. Time would appear to slow down for external observers, and once crossing the event horizon, it would be doomed to fall into the singularity beyond any hope of escape.